So for part C, Rohan's friend suggests that they use the following loss function and the stochastic gradient descent instead. And we're given this loss function. And this loss function has two parameters, theta 0 and theta 1. And pushing aside about this new loss function, James and Rohan decide to proceed and see what the optimal theta 0 and theta 1 estimates are after one iteration using the following row of data. And they pick the following starting values: theta 0, theta 1, and set the learning rate to alpha equals 0.1. And so what is important to remember is that for the gradient descent update rule, it's theta t plus 1 is equal to, if you can recall, theta t minus alpha, the gradient vector of the loss function, and you plug in theta t. And since we need the gradient vector, we have to find a partial derivative with respect to theta 0 and theta 1 for this loss function. So let's do that. The partial derivative of theta 0 is, if I can look at it, including the negative, would be negative 1 over theta 0 minus theta 1 xi. So let's plug that in. Bloop, bloop, bloop. And with respect to theta 1, it should be, oh, this should be a star, by the way. It looks like a theta. Negative, because it's negative, is theta 0 xi. So let's plug that in. Theta 0 xi. It's too big. Mine make it too big. So now that we have this, we just plug this into here for theta 0, and then plug this into here for theta 1. And so to solve for the next step for theta 0, so 1/5 step, we plug that in. That theta 0 should be given, which is 1, minus the alpha, which is 0.1, and then you plug the loss function in, or this thing in, so negative 1 over 1 minus 2, because theta 1 is 2, and xi is 3, so 3 times 3, which is equal to 1 minus 0.1 negative 7, which is equal to 1.7. This does not look like a 1. My apologies. This is a 1. This is 7. And now we solve for theta 1. Should be the same process. We put theta 1 first instead. That should be 2 minus 0.1, and then the loss function, which should be negative 1 times xi, which is 3, which is equal to 2 plus 0.3, which is equal to 2.3. And yeah, we have that theta t, or theta, the next step should be equal to 1.7 and 2.3, or theta 1 0 should be this, and theta 1 1 should be this. And now for part D, in general, which of the following statement is true? So initial parameter values do not affect the gradient descent convergence. This is false, because let's say we have, like, let me build this mountain, like So let's say the mountain goes here, right? If we start right here, we're all set, you know, it's easier. But if we start right here, it's going to take more time. So it does affect the descent convergence. If gradient descent process converge at a local minimum, then it must also have converged at a global minimum. This is false. There's no guarantee that it's a local minimum, that the local minimum is a global minimum unless we know the loss function, unless we know that the loss function is convex. So if it's like this, that's cool. But imagine this three-dimensional mountain where there's like multiple mountains, right? So there's just multiple minimums that would not be satisfied. The learning rate affects the speed of the gradient descent process and whether or not the model converges. Yes, this is true. The learning rate affects both the speed of the gradient descent process and whether or not the model converges. So if it's too large, it may cause the algorithm to bounce back and forth and just never converge. Negative values are an appropriate choice for learning rate. This is false. Because we want to reduce the step we're in, so we should not use negative values. And for each update of data may jump back and forth between two sides of optimal data. Yeah, that's true. Certain choices of a learning rate may cause each update of data to jump back and forth between the two sides of the optimal data hat. And this is also possible if one is using stochastic or mini batch gradient descent. Now for part E, in the case that the validation and test performance are significantly worse than the training performance, which of the following statements can explain this behavior? So option 1 is not correct because the model is expensive enough as exhilarated by the high training performance. And option 2 is incorrect because there appears to be some kind of pattern, otherwise the training performance would not be that high. And for option 3, it is correct since our validation or test performance is lower. It might be possible that our model fitted to the variance present in our training data. For option 4, it is also correct because if there's a mismatch between our training or validation and our testing sets, it can lead to this result. And yeah, for part F, which the following statements about regularization are true, assume we're using OLS. Option 1, L1 regularization is more likely to lead to a solution in which the coefficients are set to 0 than L2 regularization. This is true because L1 loss promotes more sparsity. For this part, it's explained in lecture 15, so I would highly encourage you to check that out. Option 2 is false. L2 uses a Euclidean norm, which has a square term, and vectors with larger values will have a larger norm than those with smaller values, leading them to be more penalized. For option 3, this is true, that L2 regularization has a closed form solution while L1 regularization does not. This is just like something to just know. It's also from lecture 15. And option 4, this is false because regularization might reduce the training performance. And is this it? Okay, yeah. So for G, you decide to use two hyperparameters, the learning rate and the regularization penalty. And you have 3 choices of the learning rate and 3 choices of lambda, or the regularization penalty. And we perform a 5-fold cross validation to choose the best pair of hyperparameters. And so we have 5 of these batches, and we basically split the validation data 5 times to get as much coverage as possible. And so we're doing this 5 times, right? And we're doing it for each combination of alpha and lambda. And so what's the total combination of these? It's 3 times 3. So there's 9 possible combinations of alpha and lambda to use. And since there's 5, like for each alpha and lambda set, we do the cross validation fold 5 times. So 9 times 5 equals 45. And that's how we get 45. And yeah, is that it? Yeah, that's it.